The earth has music for those who listen. Good day, everyone. So, before we proceed with this presentation, let's take a moment to appreciate the dynamic nature of our planet. As Shakespeare reminds us, the earth communicates through various phenomena. And today, we will focus on one of its less obvious yet powerful forms of communication: infrasound. Understanding this music of the earth is crucial for identifying natural events like volcanic eruptions. Today, I will be presenting on the research paper Monitoring of Indonesian Volcanoes with the IS06 infrasound array by Gary and the other authors listed on the slide. This study investigates the capability of long-range infrasound monitoring using the IS06 array to detect volcanic eruptions in Indonesia, a region with significant aviation activity and a large number of active volcanoes. This highlights the need for effective monitoring systems. Volcano monitoring is crucial for mitigating the hazards associated with volcanic eruptions, particularly for aviation safety. Volcanic ash can cause severe damage to aircraft, including engine failure, due to the melting and abrasion of ash within the turbines. As global air traffic continues to increase, so does the probability of encountering volcanic ash clouds. To address this hazard, the established International Civil Aviation Organization built the Volcanic Ash Advisory Centers. These centers provide timely warnings to aviation users by collecting information from various sources including volcano observatories, meteorological officers, satellite images, and pilot reports. However, volcano monitoring presents its own set of challenges. Traditional volcano monitoring methods face several limitations. Ground-based observations can be challenging, especially for remote volcanoes, and satellite monitoring is often hindered by meteorological cloud cover. This is a significant issue, as it can obscure critical pre-eruption signals and the initial stages of an eruption. Infrasound monitoring offers a valuable complementary approach. Infrasound waves, which are low frequency sound waves, can propagate over long distances through the atmosphere, enabling the remote detection of volcanic eruptions, even when visual observation is obstructed. One such approach is infrasound monitoring. Volcanic eruptions generate infrasound waves through the rapid release of pressurized gas and material into the atmosphere. These low-frequency sound waves, typically below 20 Hz, can travel hundreds to thousands of kilometers due to their ability to propagate within atmospheric waveguides. The International Monitoring System, established by the Comprehensive Nuclear Test Ban Treaty Organization to monitor nuclear explosions, also provides a valuable resource for detecting and studying volcanic infrasound. The IMS infrasound network offers continuous data acquisition, which is crucial for timely detection of volcanic eruptions. This study focuses on the IS06 infrasound array, which, as you can see here in the figure, is located on the Cocos Island, south of Sumatra, Indonesia. The researchers strategically placed the array here to monitor a cluster of active volcanoes in the Indonesian arc. Notice that the study focuses on volcanoes within this 2,000-kilometer radius of the IS06 array. This 2,000-kilometer distance was chosen because, while infrasound can travel much farther, the travel time increases with distance. Beyond this range, the delay in signal arrival would significantly limit the effectiveness of infrasound monitoring as a real-time warning system, especially crucial for aviation safety. The volcanoes selected for the study, a total of 11, were chosen based on their activity during the period of interest, from 2012 to 2019. The study involves a four-step process: initial signal detection using array processing techniques, followed by corrections for atmospheric propagation effects, then the calculation of the infrasound parameter or the IP to quantify signal strength. And finally, the system can trigger an alert if the IP crosses a critical threshold. Let's take a closer look at the first step, detection, on the next slide. Array processing is crucial for distinguishing infrasound signals from background noise. By analyzing the arrival times of infrasound waves at different sensors in an array, researchers can determine the direction and apparent velocity of the source. This helps isolate signals that are volcanic in origin. A key metric used in this process is the infrasound parameter, or IP, which quantifies eruption strength. The IP is calculated from the signal's amplitude and its persistency over a specific time window. Essentially, a higher IP reflects stronger and more sustained eruptive activity. This figure shows actual data recorded by the IS06 infrasound array during the December 2018 Anak eruption. So at the top figure, we see the infrasound pressure amplitude measured in pascals. A sharp increase starts on December 22, continuing over several days. This dense clusters of points indicate strong and sustained eruptive activity as picked up by the array. In the middle figure, the back azimuth or signal direction remains around 55 degrees, which aligns with the known location of Anak Krakatau. This stable direction confirms the origin of the sound. Lastly, the last figure at the bottom, the apparent velocity remains consistent, supporting the conclusion that the wave propagated through the stratosphere, a characteristic of volcanic infrasound and not a local noise. Altogether, this data demonstrate how infrasound arrays like the IS06 can remotely identify explosive volcanic activity over distances exceeding 1,000 kilometers. Having understood how the signals were identified and verified, we will now take a look at how the eruption timeline unfolded through the changes in the infrasound parameter over time. This graph shows the eruption evolved across the second half of December 2018, using the infrasound parameter as a time series. So, this major peak on December 22 marks the main eruptive phase. You will remember this in the same event we saw in detail earlier with the signal direction and pressure data. So what's interesting here is that the IP stays elevated in the following days, though with some fluctuations. This tells us the eruption didn't end immediately. It continued at varying intensities over time. By tracking how the IP rises and falls, the system doesn't just detect that an eruption happened. It gives insight into how long it lasted and how intense it was. This is specifically useful when the volcano is covered by clouds or located far from visual monitoring system. Let's zoom out and examine how well the systems perform across multiple eruptions from different Indonesian volcanoes. This graph shows how the infrasound parameter or IP changed over time for each volcano between the 2012 and 2019. In this figure, blue sections mean that the IP stayed below the alert threshold, meaning no eruption was flagged. On the other hand, red sections indicate that the IP crossed the threshold and the system interpreted it as an ongoing explosive eruption. As this will be frequently mentioned, VEI or Volcanic Explosibility Index rates eruptions from 0 to 8. The higher the number, the larger and more violent the eruption. So let's walk through some examples and see how well the system did. First, the Kelot in 2014, which had a VEI of 4, a major Plinian eruption. As you can see, there's a thick, uninterrupted red bar showing that the system clearly recognized the eruption and kept the alert active for several hours. This was a textbook case. High intensity, strong propagation, and a clean, reliable detection. According to the paper, the IV for Kelot exceeded the threshold with no false alerts and tracked the event accurately from a distance of 1,750 kilometers. Second, the Anak Krakatau in 2018, which we already explored earlier. It had a VEI of 3, and again we see a long stretch of red showing sustained activity. This was the peak that triggered a tsunami, and what's important here is that the IP didn't just detect the eruption. It tracked its intensity for several days, even when visual observation was limited by weather. This case also supports the early warning potential of long-range infrasound monitoring. Now for something different, we have the Sinabung, also with VEI for activity during 2018 and 2019. But surprisingly, this eruption was not detected by the IS06 array. Most of the row is blue, which means the IP stayed below threshold. Why? As the authors explain, the issue wasn't eruption strength, but poor atmospheric propagation. Stratospheric winds diverted the infrasound energy away from the station, So the system couldn't pick it up, proving that eruption strength alone isn't enough. The direction and seasonality of sound propagation also matter. Next, take a look at Semeru, a volcano with VEI-2 activity, meaning smaller, short-lived explosions. These bursts of IP were detected, but according to the paper, many were actually false alerts. As you can see, there's a short dotted red spikes along the road. This happened because Semeru shares almost the same back azimuth with nearby volcanoes like Yalut, which made it hard for the system to pinpoint the true source of the signal. So lastly, the Merapi. During the studies period, it had a low-level activity, mostly dome collapses and weak ash plumes. The IP did rise briefly, but only for about 21 minutes, which wasn't enough to trigger an alert. Its signals also overlap with neighboring vents, increasing the risk of false detection. The authors explained that in these cases, the system is more likely to stay silent unless the eruption is stronger or more sustained. These limitations become even clearer when we compare the system's response across multiple volcanoes. For instance, Kelot was detected clearly and continuously, but eruptions like the one from Sinabung, were not recorded by the system, not because of eruption size, but because the infrasound signal failed to reach the station due to unfavorable propagation conditions. We also see false alarms in cases like Semeru and Rayong, where signals from nearby volcanoes overlap in direction, causing confusion. To solve this, a new approach was introduced, shown here on the right. Instead of forcing the system to always identify the exact volcano, the monitoring area is divided into 9 regional sectors based on the direction or back azimuth of the signal. So when an infrasound signal crosses the detection threshold, the system doesn't need to pinpoint the exact volcano. It can simply say an event is happening in this sector. This is especially useful in Indonesia, where many volcanoes are close together and often erupt with similar patterns. This sector-based strategy helps avoid confusion and still gives aviation authorities enough information to monitor and respond. Even if the source isn't clear, the alert still points to the right region, which is often enough to trigger further observations or warnings. So to wrap it up, the study not only showed the strength of long-range infrasound monitoring, but also recognized its limit and responded with a smart, realistic solution to improve reliability. To conclude, this study highlights how infrasound monitoring can support volcano surveillance, especially in archipelagic regions like Indonesia, where direct observation is often limited. The system works best for larger sustained eruptions, typically those rated VEI 3 and 4, which are also the most hazardous to air traffic and nearby population. In this case, the IP consistently exceeds the alert threshold, providing clear and timely detection. However, the study also shows important limitations. Short-lived eruptions, smaller VEI events, and unfavorable stereoscopic conditions can cause the system to either miss a real event or raise a false alert, especially when multiple volcanoes share the same directional path to the array. So, to address these challenges, the sector-based monitoring approach was introduced. This method reduces confusion by tracking regional activity instead of focusing on a single volcano. So, overall, infrasound-based detection is a reliable, remote sensing tool that enhances early warning system, particularly when other methods like satellite or visual observation are unavailable. But for maximum effectiveness, it could be or it should be used together with other monitoring technologies. So infrasound doesn't just tell us that something happened. It tells us when, how long, and from where even if the eruption is hidden from view. And that's all. Thank you.